Everyone, this is Jeremy Myers, and I'm going to give you a brief introduction to the paper DeftNN Addressing Bottlenecks for Deep Neural Network Execution on GPUs via Synapse Vector Elimination in Near Compute Data Fission. There will be many more details in the presentation on Tuesday, but to keep this between 5 and 7 minutes, I'm just going to have to give a very, very quick overview of everything that's going on with this paper. So in general, machine learning is taking advantage of deep neural networks. Neural networks are perfectly paired for operations with GPGPUs due to the computational complexity of what happens in a deep neural network. But the issue is that training them is very computationally expensive, and there's a high demand for optimizing the training process. If you're not familiar with neural network, it's okay. I will give you a little bit more of a deeper understanding on Tuesday, but basically it's a collection of layers that there's some mapping that goes between them, and information is propagated through the system. What makes it a deep neural network is that there's hundreds, if not thousands, and hundreds of thousands and millions of nodes and layers that pass information and process the data as it moves through the network. Something that is really important, since many real-world applications, these neural networks grow to these huge sizes, we want to reduce the size. So we do that for two reasons. We can reduce the computational complexity, and we reduce the memory footprint. And both of those things will result in improved throughput for the neural network. Memory remains the bottleneck simply because we have optimized matrix multiplication code. So the paper, it prunes deep neural networks by removing parameters that don't contribute to the network, and they refer to this as synapse vector elimination. So let's look at the whole system. You train a deep neural network, you look for groups of non-contributing synapses, you retrain the deep neural network, and then at runtime, so all that happens offline, then at runtime you remove those synapse vectors, and as a further optimizing step, we quantize the input data by casting it to a different data type. So pruning happens. We do this because, like I said, we want to reduce the computational complexity and improve the throughput. But when we do it and we're just selecting random weights, we introduce sparsity into the system. And the whole idea with the GPGPU and a deep neural network working together is that the GPGPU can take advantage of wide vector units. And so introducing sparsity really, really ruins a lot of the performance improvement that you get. So the DeftNN system basically works offline to shrink the number of synapses that are going by collectively throwing out an architecturally efficient number of them. So rather than throwing out 1 or 2, they'll throw out 10, but by throwing out 10, you actually have better improved performance. So it's a two-step transformation. We have to change the order of the vectors in each synapse group, and then we truncate the matrix. So we find our non-contributing synapse vectors based on correlation. Basically, if the correlation is high enough, then we keep them, and if it falls below the threshold, then we mark them to be discarded. And then we partition the matrix that we have, and we just select the vectors that are to be kept and move them to the left, and we take the vectors that are to be discarded and we move them to the right, and then we cut off the right-hand side and throw it away. Furthermore, we're going to cast the data into different data types. So the authors of this paper play around with 3 different types, and then they perform some hardware accelerations, and these are actual ALU proposals that can go ahead and do the casting in a much more efficient manner than methods that we've seen currently. The nice thing about this is that a lot of research that's going on right now is showing great results for casting data from something like single precision down to 8-bit or 4-bit or even 2-bit. So there's a lot of promise in this field. So it was a really smart idea on the author's part to go down this route. The system performs very, very well. They see about a 200% improvement in performance with the whole system under consideration. That includes Synapse vector elimination, changing the data type on chip, and basically taking advantage of on-chip memory bandwidth, basically removing that bottleneck. So they do it on 6 different neural networks with several different data sets. I'll go over some of the details of the performance on Tuesday, but in general, the proposed changes that they have, the proposed data types, the quantizations, all show very, very good promise, and leads to a good motivation for hardware vendors to make some of these changes. Again, I'll go over some of these details, but basically their concept of data fission by including a new ALU type unit on chip holds a lot of promise for improved performance. So in summary, the paper discusses the following things. We reduce the network topology by synapse vector elimination, and this improves performance by reducing the number of computations, decreasing the dimensionality of the weights will improve performance. They introduce a new data fission unit, which is similar to an ALU, and basically this hardware accelerated data really improves performance by several times. They discuss that performance gains at small accuracy losses can be achieved by lowering this correlation parameter. Basically, if you make it more restrictive, you give up just a small amount of accuracy, but you improve the performance by several factors. And as a real-world application, the implementation for deep neural networks that is packaged with CUDA code, the cuDNN, DeftNN works very well with cuDNN. So a couple of things that I thought were strengths and weaknesses about this paper. I think that it's a really smart way of addressing the dimensionality reduction. Frequently, you see dimensionality reduction by reducing the size of the data, but this actually applies similar techniques and reduces the dimensionality of the network topology in a similar analogous way. Also, I thought it was very nice that they propose this dynamic quantization technique, and they give steps on how to compute the new quantized data. And it looks like the hardware proposals that they have are very promising. On the other hand, I found that some of their details are left fairly vague. A lot of their support for their hardware changes were performed on an in-house GPU simulator, but they don't give any details on whether or not it's been validated. So we don't even know whether or not it does as well as it says it does, because we simply don't know. And some of the underlying statistics assumptions are a little bit fuzzy, and in particular, there's more robust methods that are common in machine learning that can be implemented that might improve synapse vector elimination. So what I propose are these bits of future work. The first would be robust vector synapse elimination. In a first pass recommendation, I'd say that using either principal component analysis or kernel PCA, two well-known techniques can be implemented efficiently for robust vector synapse elimination. So the reason I recommend this is because we can let PCA or KPCA, depending on the implementation, eliminate the vectors for us based on their variance rather than arbitrarily going through checking whether or not they correspond to some correlation. Basically, we look for gaps in the spectrum of the synapse vectors through a matrix decomposition, and we let the data tell us what to throw out. And it just comes from the assumption that that's a smarter way to do it. So another part of this, an advantage, is that we can skip the vector reordering stage. PCA and kernel PCA does this naturally. The results are in descending order. So depending on if there's no gaps, then you simply choose a place to cut it off. If there are gaps, then you can allow the program to cut it off where the gaps occur. Or if you have some sort of architectural concerns, you want to optimize for what fits in the cache or in the memory, or optimize for bandwidth, you can choose a set place to cut off the data. So in my opinion, it's quite a bit more flexible. And furthermore, PCA, KPCA are based on singular value decomposition, which we know to be mathematically optimal for coming up with a low rank approximation of a matrix. And the other extension I have is something that is just been a common theme so far that we've seen, is that deep neural networks have high accuracy with low precision data. So if they can extend the support to 1 to 4 bit, and they do include an 8-bit floating point implementation, but also of integer types, I think that it would be really interesting to see what sorts of performance improvements can be gained from the whole spectrum of different data types. Anyway, so that was a very, very brief overview of this paper. I will give much greater details on Tuesday, and I look forward to presenting and hearing questions from the audience.